Hi, in this video I'm going to go through various papers showing the work of reinforcement learning in compiler optimization. I'm going to give a brief summary of the papers, and at the end I put the references, and also the references will be available in the description of this video. In this paper, a reinforcement learning environment is developed for compiler optimization. It makes it easier for researchers to develop reinforcement learning agents for particular compiler optimization problems. In this paper, 3 problems are shown, but more problems can be added to the compiler gym. And it is targeting LLVM, GCC, and CUDA, but could be extended as well for other compilers. So the compiler gym environment is going to abstract all the hard details, all the complications of the compiler into a API that is compatible with reinforcement learning. It's a Python API that makes it easier to basically develop a reinforcement learning agent, but also can be used to implement a search algorithm or use handcrafted heuristics as well. So it's gonna provide the action, which is basically depending on the problem, and it's gonna give the observation, also depend on the problem, the reward as well. You can imagine it could be runtime execution, it could be size of code, memory, etc., power consumption, and also you have an action space that is used for the action, and it also has a signal to tell you if the episode is over or not. For example, you have a crash, assertion, or error. So this was done in collaboration between Hugh Letter, a professor from University of Edinburgh, in collaboration with Meta, with Facebook, Chris Cumming, who also working here, work with Hugh in the same university. And these are the 3 problems that they're tackling. One of them is for LLVM phase ordering. Phase ordering is a problem that has been in the past trying to be solved using deep learning, and this time is with reinforcement learning, although this is not the only paper doing so. So the actions is going to be the 124 optimizations passes that LLVM has, and the reward is the code size. Could be a code size, binary size, runtime, or a combination of them. And the observation is a vector for the code features, and a representation of the code graph. So for the GCC, is the problem tackled is flag tuning. So the action is going to be which flags are you going to use. The reward can be similar, could be size of code, runtime, and the observation this time is going to be more the binary side. Also, there's a problem of CUDA loop nest code generation, and the actions will be is the scheduling, the rewards are the flops, and the observation is the loop structure. And you can imagine that other problems can be added. For example, a particular optimization has certain parameters that need to be fine-tuned. This could be easily added here as well. This paper presents Supersonic, a meta-optimizer to do automatic selection of reinforcement learning algorithms and hyperparameter optimization for compiler optimization problems. The paper comes from Northwest University in China in collaboration with Meta AI Research and University of Leeds. Initially, you have a set of reinforcement learning algorithms to choose from, and one is selected automatically. They use, to do that selection process, they use multi-armed bandit-based policy search and multitask learning. Once the reinforcement learning architecture is chosen, they do hyperparameter optimization, the tuning, and then finally do the deployment. It is interesting that Chris Cumming and Hugh Letter, that appear under Meta AI, they were part of the University of Edinburgh, and they work for a long time in the intersection between artificial intelligence and compiler optimization. Supersonic chooses from a list of 23 different algorithms, reinforcement learning algorithms, but also it chooses between actions like compiler option, code transformations, also the reward, and the modeling method. And basically they have a finite set for these options, and they choose between them. They could also include a transition function for the state, for the probability of going from one state to another. And they build on top of compiler gym. Compiler gym, I think, is used downstream in the pipeline of their workflow, and also they use RLlib. Also, like compiler gym, they use Python and gRPC for communication. To model the reinforcement learning problem for selecting the reinforcement learning architecture, they use multi-arm bandit instead of a Markov decision process. This multi-arm bandit is simpler, and the way that it goes is that after n trials, they determine which of the k reinforcement learning configurations to use for the given problem. They also, one advantage that reinforcement learning has over evolutionary algorithms is that they can reuse knowledge from other tasks to speed up the search, like something like transfer learning. And in contrast to evolutionary algorithms that must start from the scratch always. But he also mentions that evolutionary algorithms have lower runtime overhead, and the author suggests that evolutionary algorithms and reinforcement learning could be combined as a future work. For the supersonic, asynchronous advantage actor critic is used, which can be trained in parallel asynchronously. I understand that this is something like what MATLAB does for asynchronous training, which is sending a set of workers to gain the experiences in parallel and then do the weight update in the synchronizing worker. This parallelization of training is built on done using the open source multitask learning framework, and they use Docker for this work. The reinforcement learning agent that is used to select the reinforcement learning architecture, the A3C, uses a ResNet CNN followed by an LSTM, and for the actor and critic. And one problem that they saw was that high reward tasks were getting more hardware resources, and a trick that they did to balance this is to put normalization layers on the actor. And you can see this supersonic framework as a hierarchical reinforcement learning problems, in which at the top you have the selection of the reinforcement learning architecture, then followed by the reinforcement learning hyperparameter optimization, and then the reinforcement learning training for the compiler problem itself. So for the top agent, the reinforcement learning agent selection, the action is going to be the reinforcement learning algorithm chosen, the policy. The observation are going to be the last 20 actions, and the critic observation is the same, but also including the accumulative reward across benchmarks. Then once you select the reinforcement learning architecture, which could be, these are some of the examples, MCTS, PPO, DQN, Q-learning. Then after you select one of those, you have to do the hyperparameter tuning, and the action is going to be the parameters chosen for the agent. And you can see that the hyperparameters are going to be different for each agent. For example, PPO has entropy coefficient. Some common parameters include mini batch size, learning rates, etc. DQN has Adam epsilon, clip gradients, and so on. So once you choose the hyperparameters, then you do the actual training of the reinforcement learning with the hyperparameters on the compiler optimization problem, and the action and observation are going to depend on the problem compiler optimization problem itself. We can see in the right the API for supersonic, in which you have the constructor which takes the list of states to consider, the list of transfer functions, actions, the list of actions, rewards, and algorithms, reinforcement learning algorithms to choose from. And at the bottom, you see how it is called. You call the constructor with all the possibilities, and you can see in the left that for states you can choose from word2vec, doc2vec, Colbert. You have a set of neural networks to choose from. You had a set of rewards to choose from, a set of algorithms, reinforcement learning algorithms like MCTS, PPO, DQ, and Q-learning to choose from, and actions to choose from. So basically you pass all that into a constructor, and then you call the policy search with the benchmark list and specifying the number of trials. The user has to provide a run method to do the actual compilation and execution on the compiler, and basically this result is stored in a database that can contain the action history, rewards, execution outputs. And the author mentions that decoupling the reinforcement learning exploration and measurements allow for parallel execution of measurements and possibly executing across different machines. And this reminds me that MATLAB Reinforcement Learning Toolbox has something similar for asynchronous parallel training as well. The author is going to compare again do the evaluation with 4 different use cases. One of them is image processing, optimizing image processing pipeline, neural network code optimization, code size reduction, and super optimization. In the middle column, you're gonna see the what is gonna be supersonic evaluated against. In the case of image processing pipeline, it's gonna go against Halide, and these autoschedulers include the Adams 2019, which I understand could be the best autoscheduler for Halide. Reference number 3 is the Adams 2019 paper. Also, it compares against reinforcement learning for Halide. And also for neural network, it compares against TVM, auto TVM. There's a reference to Answer, but Answer is not mentioned in the paper, and the reference for Answer is 92, so it might not be, I understand it might not be comparing against Answer, but I could be wrong. It doesn't mention Bansor, which is an improved version of the Answer autoscheduler from TVM using reinforcement learning. That is not mentioned in the paper. And code size reduction is comparing against Open Compiler Gym. And you can see in the right column that the search space for the first two problems is smaller, but getting the compiler results is more takes more time. So it's cheaper, easier to get the samples from these two use cases. And you can see in the table on the right the different states to choose from and the reward function. And you can see that for each problem there's only one state and only one reward, which makes sense. I didn't thought it makes sense to choose a state and a reward for a particular problem because I thought that that was fixed, and this seemed to confirm what I suspected, that you don't actually choose. For example, for image processing you get the manual features, for deep learning you get doc2vec, for code size you get hash of action history, and for the reward you get the function output, and for the image processing and deep learning you get the relative measure like speed up. Well, you have some options in here that you can choose from, so probably you actually do some choosing. Okay, let's take a closer look at the different benchmarking cases of the paper. The first one is Halide image pipeline optimization. They're comparing against Halide reinforcement learning, which uses PPO, and Supersonic is using Monte Carlo tree search. The actions are going to be applying tiling vectorization on existing scheduling sequence templates. So this is not like Adams. Adams basically uses a cost model to choose one scheduling primitive at a time and its parameters, and it goes assembling the sequence of scheduling primitives for Halide. For this one, there's a template, and they add remove primitives, also increase and decrease primitive option values. So basically it's like a mutation rather than assembly from the scratch a sequence of scheduling primitives. For the observation, Supersonic is using the runtime performance after compiling the program, and captures the already applied scheduling primitives as a hash value, as a hash function. And Halide reinforcement learning is using also getting the sequence of applied scheduling primitives, but not as a hash, and it doesn't seem to use the runtime performance. That's weird. And okay, so that's for Halide. For neural network code optimization, they are using the TVM compiler and try to select a good schedule to reduce the execution time, and the action and observation are similar to Halide. It's a similar problem. You're basically doing an autoscheduler and selecting the optimal scheduling primitives. The TVM schedulers are similar to those of Halide. For the LLVM code size reduction, they are competing. Supersonic is competing against compiler gym in the evaluation, but also it uses compiler gym. The actions is a set of 123 semantic preserving passes of LLVM, and they could run in any order, and even they could repeat passes as well. And the observation is a ratio of instruction count over OS size that is platform independent. The fourth problem, and final, is the super optimization, which is an LLVM problem. It's a classical compiler optimization task that finds the valid code sequence to maximize the performance of a loop-free sequence of instructions. You can see an example in the right where we have a set of LLVM instructions, and they get significantly simplified by using the pop CNTL instruction in here. And that is done using the Stoch hacker kernel. So the actions are going to be all the instruction level transformations supported by Stoch, and this includes replacing the opcode, operand instruction, as well as inserting, replacing, or swapping instructions. And they didn't mention the observation, but I assume it could be runtime performance. And remember that Supersonic, for each of these 4 problems, are gonna choose the reinforcement learning architecture. So for this particular super optimization problem, Supersonic shows PPO. For the other 3, image processing, deep learning, and code size reduction, Supersonic shows Monte Carlo tree search. In these results, you see the performance evaluation for the first 2 problems, image processing and deep learning. The image processing is on the left and deep learning is on the right. So you can see that for image processing, you're comparing against OpenTuner, Haleit Reinforcement Learning, Adams 2019 Autoscaler, and Supersonic. And these 2 are the best performing, but after Supersonic. Supersonic is beating in all the cases. And you can see that Adams, it's interesting that Adams is going to beat the Haleit Reinforcement Learning in AMD, but not in Intel. Perhaps Adams 2019 is using a deep learning based cost model, so it might have been training AMD but not in Intel. That could be the cause why it's not winning to Haleit RL in here. And yeah, you can see that regardless of the tuning time or tuning iterations, the Supersonic is able to win in both of them, and that's basically an advantage of reinforcement learning. It provides this portability, and also you can see the same portability in the deep learning results. And in here they're comparing one of the best performing is Chameleon, which is a recent paper. And yeah, basically in AMD, in Intel, you get the similar results that Supersonic is beating the existing options. In here you see the results for the other final 2 problems, the code size reduction. And remember that for code size reduction, you choose a set of 123 compiler passes, which you can use multiple times and in any order. And you can see, and here the Supersonic is being compared against compiler gym. Not only compares against compiler gym, but underneath it also uses compiler gym, similar to the other problem in super optimization, where they're using underneath Stoch, but also is comparing against Stoch. And you can see that in this problem, it's gonna beat Stoch in all the cases for AMD and Intel. And the same thing for number of iterations, tuning time, number of iterations. For the case of code size reduction, also you get similar results, beating in all cases. And one interesting thing is in this table 4, you're gonna see the compiler passes that were chosen more often by Supersonic. For example, simplify CFG, common soft expression elimination, memory SSA, GVN, global value numbering, and new GVN, and instruction combined. So these instructions, you can see these operations were rarely chosen by the compiler gym and the OpenTuner, rarely chosen. But Supersonic is using it more frequent. And the rest of the instructions, the rest of the optimizations are used 60% of the time, and the rest of the optimizations for the others, the other optimizations are used more by the other alternatives. So basically, what Supersonic found that these optimizations are really important for code size reduction. In here you can see again the 4 benchmarks using the paper and being compared where Supersonic is compared against genetic algorithms, simulated annealing, random search, and grid search. And you can see that grid search, random search, evolutionary genetic algorithm all have the same performance of Supersonic when the search space is slow, except in this one. But then as the search space increases in all of them, the Supersonic advantage is clear. A good news about the paper is that from the paper is that they plan to integrate Supersonic into the mainstream release of compiler gym, and they hope that Supersonic will be available out of the box for once the user defines the optimization tasks. In this paper from India Institute of Technology, in collaboration with Google's France office, they tackled the register allocation NP-complete problem using reinforcement learning. For their algorithm, they take into consideration register type, congruence, liveness, analysis, and interference graph with constraints that should take into consideration the liveness and the type of registers. They compare their work against LLVM's BPQP and greedy algorithms that took man-decades to develop, and they modeled, as other reinforcement learning compiler papers, they modeled the compiler optimization problem as a Markov decision process. And one thing special of this paper is that they use hierarchical reinforcement learning for register allocation, and we're going to see more details about that in a moment. And they demonstrate performance results on par with the best allocators available in LVM, and this is already a win because, though, as mentioned before, these algorithms took decades to develop, while this reinforcement learning algorithm is done pretty quick. So it not only saves development time, but also in maintenance, because the logic is in the weights of the neural networks rather than being in manually written code. And of course, the algorithm can be further improved because things like coalescing was not included. Okay, so here's a snapshot of the system. In the right, we have the reinforcement learning agents, and in the left, we have the compiler-related artifacts. So this work depends on the LLVM's MIR intermediate representation. So we have a source code that is going to be compiled and optimized, and we have the MIR functioning here, emitted by LLVM. So from that, they get the interference graph, and they have this MIR to vec, like code to vec, and from that you get the embeddings, and you can see that you get some vocabulary, and I understand that this embedding gets trained. So that is communicated to the reinforcement learning agent via this GR RPC remote. This is basically a communication protocol in which they communicate with the agent, and eventually that graph, that interference graph, and the information about the coloring and etc. is captured in this gated graph neural network that has also some embedding, and that becomes observation for the agents. So the agents, you can see the hierarchical nature in here. You have the node selector, the task selector, and splitting and coloring. The node selector is going to select the node in the graph to act upon. And once you select it, you're going to select the task to perform. So it could be splitting the node or coloring it. And then you have further agents to select how to color, what color to assign, or how to split that node, where it's going to using the dominance frontier. So that action of splitting and coloring is communicated through RPC and sent back in here, and then the graph is updated based on that. And then again, the process continues. So the updated graph is sent, and you continue processing. The agent that they are using is the proximal policy optimization. I think there's another paper that we saw before is using also PPO. And let's go in details to the reinforcement learning agent. So basically here's the well, let's tackle first the node selector agent, which we have here. The action is easy. The action is basically selecting the register to process. The reward is based on the coloring agent. Okay, let's go to the reward of the coloring agent. So it's gonna receive a positive if you color, and negative if you spill. Of course, the more spilling, the more memory you spend, so you don't want spilling. But also, you could add into the reward the less color used, the better. So you can, so basically for the splitter, there's a difference in spill weight. So there's some nodes that are better to spill than others, and that's included in the reward. The task selector is going to inherit the rewards based on the lower level task. For the observation, they don't talk about the observation, but for the node selector, you can see that the observation is the GNN. and the spill cost, the size of light ranges, information about the interference graph, I suppose. And I understand that all of these might be also having the same observation. For the task selector, the action for the task selector is basically to either to spill or color, I mentioned before. The task for the splitter is selecting the point of splitting using the dominance frontier, which is analogous to the 5 copy replacement of SSA. And the action for coloring is basically the colors available based on the constraints in your graph. So they also have a global reward based on the throughput of the generated function, so they can take consideration the performance as well, which is good. Okay, so in the terms of the layers for the GNN, for the observation, they use 2 fully connected layers, and also they use RNNs for message passing. For the actual agents to take the action, they just use fully connected layers. The node selector and splitter use 4 fully connected layers, while the task selector and coloring agents are using 3 fully connected layers, each with batch normalization. And everywhere Relic is used as the activation function, and they consider using compiler gem, but compiler gem didn't fit this problem, so they made their own gem environment, reinforcement learning environment for this problem. Okay, so for the performance numbers, you can see they took the hot functions, which I understand is the most the one that are highlight. I mean the top 5 or something like that. Or so we can see here that for the CPU of 2006, basically the greedy algorithm is able to beat the mean average and in maximum. But when you go to the 2017 CPU, then the reinforcement learning agent is able to beat it both in average and maximum. So this also speaks of an advantage of reinforcement learning, which is portability. So if their algorithm, the LLVM algorithm worked well for this particular architecture, but for here you might need more man decades, maybe not man decades, but you need manual development work to make it work well for this 2017. But for the reinforcement learning agent, you just need to retrain it. So portability is easier when you use these AI techniques. And you can see more details about each of the functions. So these are the comparison between Greedy again, and you can see that in this one in particular, Greedy performs terrible, and reinforcement learning didn't perform as bad. And in this one, the reinforcement learning performed real well. So these are highlighted particular benchmarks from the whole benchmark set. And these are the top slowdowns, and slowdowns compared to the LLVM algorithm. And you can see that it's not that bad, but let's take a look at the average, which is better. So here we have all the benchmarks, and sometimes the reinforcement learning wins, but the greedy wins more times, but in average they're almost the same. So again, also for this case, for this architecture, the similar thing happens. So again, even though reinforcement learning doesn't win significantly in terms of performance, as mentioned before, it saves development time, it saves maintenance, and it's more portable than manually written implementation. So still is a win for this type of work. In this paper, they use reinforcement learning to optimize halide schedules. Notice this paper was published in 2019, so that's the same year that the Adams 2019 halide autoscaler was released. So they're only comparing against Mujapudi of 2016. For those who are not familiar with halide, this is an example program. One of the main advantages of halide is the separation of algorithm and schedule. Schedule is the order in which the computations are made, and algorithm is the actual computation. So in this case, the most probably the most popular halide example, Blur, is used, which is a two-stage computation in which the first stage computes the horizontal blur and the second stage computes the vertical blur. So in here you can see that the schedule primitives are applied into the algorithm after the algorithm is defined. And this is what the reinforcement learning algorithm is going to determine. Okay, which scaling primitives in which order and which parameters to use for it. So at the top you can see the diagram of the reinforcement learning environment. You have the critic to determine the long time reward, and the action, which is going to be the scaling primitive and the arguments. And the reward is based on the compilation time. So you see another diagram in here, which the input is going to be the image processing pipeline, in this case the blur, scheduling options, which type of scheduling primitives you can use, and this is provided by user, but the author recognizes that this can be automated, and that should help. And then when the reinforcement learning is going to use the compiler, that is going to compile and get the execution time. So this is the bottleneck again in this process. And yeah, so that's basically in a nutshell what they're doing. So again, they're using a PPO as using OpenAI. As mentioned before, the schedule, allowed schedules are provided by the user, but they recognize that this can be automated, and the actions are going to be the scheduling primitives and the arguments for that particular schedule. And you for scheduling primitives like compute at, store at, those depend on the stage. So the stage is important in part of the action. And the reward is the runtime, and also you can get a compilation error. And basically they depend on the Halide compiler, so they guarantee correctness. And the reward, you can see that if you have a better runtime, then you're gonna get a penalty. I understand, because let's say that the current one is higher, so then you have a negative penalty in here. But if you have less, then you're gonna get a reward. Should get a reward, and it's normalized against the start runtime. So if the current time, but that's for the case the previous one is higher than the current one. So if that is the case, you're gonna get a positive. Actually, you get a positive reward in here, but also you get a 0 if it is equal or larger than the previous one. So that should be a negative in here. And of course, if you get a compilation error, you get a penalty. And the environment is done using OpenAI in Python, and of course Halide is in C++. So they're using gRPC for communication between Python and Halide. So here they show a tree showing the possible alternatives for a schedule that the user must provide. And in the right, you can see an example of a schedule for the blur algorithm. You can see that you have the definition for the blur, so you can have all these options like tile, split, and you have a set of split factors that you can apply. So this is how you provide the scale, but again, this can be provided automatically. So yeah, so this is another way of viewing this. Here are some of the results from the paper, and it compared against Mulapuli because Adams was not available, and also the bottleneck of this. The bottleneck is the compilation time of Halide, and yeah, maybe something of that could be used. Maybe having a neural network that predicts the execution time could help in the reinforcement learning. I mean, not using the compiler every time. And also here you can see a sample for they use only 3 pipelines: blur, Harris corner detection, and interpolation. And you can see that in the columns you have 3 types of images. I assume that the last one is the biggest and this is smallest. And you can see that for the case of the blur, which is a problem that is beaten to death by the Halide community, you can see that Mulapudi outperforms slightly in the middle image, but in CPU. But for the other sizes, the reinforcement learning autoscaler won. But also, Mulapudi does not work with GPU. And in that case, the reinforcement learning clearly beat the hand optimized version of the user. So the same goes for Harris corner detection. In all cases, the reinforcement learning is beating both Mulapudi and also the hand-optimized version of Harris corner detection in both CPU and GPU. And for the interpolation, Mulapudi performed better only in one image, and the hand tune basically outperforms in 2 out of 3 images. But let's take a look at this. Is how it looks for the blur with PPO agent and the hand tune. And this is for CPU and GPU. You can see that the PPO is using a roll parallel bound. It's not using vectorized, it's not using computed, and we know that those are important for the blur algorithm. So something is missing in here. So that shows that these can further be improved and you could get better results. And for the case of the GPU, it's basically using GPU tile. For some reason it didn't use tile in here as well. So, but the one thing that the advantage of this is that it was easy to use a different target. So for example, if Muyapudi or Adams want to use GPU, they have to do additional work. So in this work, there was practically no additional work to try on GPU, so it can easily be used to optimize for TPU or any other hardware. So that's one of the advantages of reinforcement learning. But still, there's some improvement that still needs to be done in here. This paper from Huawei presents Bansor, which is an improvement over the Answer autoscaler of TVM. TVM is a domain-specific language targeted for deep learning. The Answer autoscaler uses genetic algorithm for the search, and in this paper they don't replace it but slightly improve it by using Stochastic Bandit reinforcement learning on it. So in the future, as a future direction, they mentioned that they plan to use Monte Carlo tree search to fully replace the evolutionary search algorithm. And in the right, you can see a sample of the Answer original algorithm. They use sketches in which the genetic algorithm picks the best performing ones, and you can see that this is the high-level matrix multiplication algorithm and the naive implementation on the right. And you have different schedules, tilings for this matrix multiplication. So there's some varieties of tiling, and basically the algorithm selects on them. So we can see in the writing here the original Answer genetic algorithm search that they use, and somewhere here they introduce the Stochastic Bandit reinforcement learning algorithm. It could be on the selection in here, line 7, it could be here, but they don't exactly specify how and where. We can see in the left the reward function that they used. The reward function is based on the latency to generate the fastest schedule, and in here T is the small time window and F is the number of floating point operations. So you take the gradient and you make a ratio with the maximum floating point operations. So they also use the concept of upper bound of confidence to balance the exploration and exploitation, which is very important in reinforcement learning. You can see the factor in here plus the reward. So here are the results that they got. They normalized the results, so the best performing one is going to get a 1.0, and you can see that almost in all cases Bansor is above Answer. Answer is the orange one and Bansor is the blue one. So in the left we only see results in CPU. You can see that the benchmarks that they use are based on convolution, matrix multiplication, which is two of the most important operations in deep learning, and there's a lot of focus on that. You can see in this place the decodification of the benchmarks. So you have C convolution 1D, convolution 2D, convolution 3D, general matrix multiplication, and transpose convolution, etc. Or group convolution as well should be depthwise convolution. Group convolution is also there. So you can see that for batch size of 1 and batch size of 16, Bansor clearly outperforms on CPU Answer. But also there's comparison on CPU and GPU, and you can see that for batch size of 1, Bansor always beats, but there's only one exception in the convolution layer. So here the benchmarks are the convolution at CPU, convolution at GPU. That's where Answer performs better in here. And Also, there's this layer, TBS, which is a composition of various transposes, batch normalization, batch matrix multiplication, and softmax function. Okay, so in here we can see also that a Bansor tends to perform converge faster. This paper is called Target Independent XLA Optimization using Reinforcement Learning, coming mostly from Amazon and also from University of California, San Diego. Is focused on using reinforcement learning to do the phase ordering of high-level operations in TensorFlow. So they optimize a DNN at this high level in a target-independent manner. They cannot use compiler gym because compiler gym is focused on LLVM, and this is a whole different compiler domain. So they implemented their own XLA gym based on OpenAI, and the reward is going to be it can be the instruction count, the XLA operation count, and the graph size. They saw 13% improvement in operation count reduction on a benchmark of GPT-2 training graphs, and 10% on a diverse benchmark that includes GPT-2, BERT, ResNet, and others. So they use geometric mean for their against AWS Neuron SDK for the results, and you can see a formula here. They also try runtime optimization, and they get about 3% in improvement. For the agents, they use 4 different agents, and PPO was the winner. And you can see here in this chart from MATLAB documentation that when you go to the right, you have more complexity and more effectiveness. If you go to the left, you get less effectiveness, but more simplicity and easier to train. And I was expecting the TRPO to perform better than the PPO, but the PPO performs better. Proximal policy optimization, and we have seen in other papers that has been the preferred agent so far. And also, like in other papers, for reinforcement learning in compilers, we can see that a Markov decision process is used to model the environment. And this in here they use a tuple of 5 elements, which is the state, observation, the action, the transition probability, which is the probability going from a given state and action to another state. The reward is going to be the negative of operation count. It could be also flops, negative of graph size, penalty for erroneous graph, etc. And the y is the probability. It's basically a reduction factor of the reward as time goes by. So basically, you want to encourage the agent to finish as soon as possible. And the observation is going to be features of the graph at a given point in time. And the action is going to be 53 high-level operations, compiler optimization passes. So this is how you control the phase ordering. So the reinforcement learning agents used are prepackaged, but if you make them custom, the author claims that if you make them custom and with domain knowledge, this can be further improved. And here you can see the API, which basically has the standard methods of making the environment, calling the reset function, and step for each step of within an episode. Pretty standard. They're using OpenAI gym, and basically you can see that PPO outperforms slightly the TRPO. TRPO did not do bad, but it was expecting to do better than PPO. And you can see that it got performance improvement up to 27% over the TensorFlow solution, over the TensorFlow alternative. And we have seen so far that reinforcement learning is beating the manual-made optimization, so which is a big improvement in terms of development time and maintenance. In this paper, they use reinforcement learning to do vectorization, and this is a collaboration from UC Berkeley and Intel. And you can see the basic idea here in this diagram, in which they have an input program which they compile in Clang LLVM, and from that they get the reward for the agent. And then as an observation for the agent, they extract the loops, use code2vec, and get the embedding to the agent. So they achieve a speed of between 1.9x to 4.73x in average, and only 3% worse than brute force solution. And you may wonder why not use brute force solution. Basically, this is like an exhaustive search for the vectorization parameters, so this is not really practical. It's just used as a reference, so to know how close you are from the optimal solution. So they use various options in addition to reinforcement learning, like decision trees, nearest neighbor search, and random search. So as a feature ideas, they suggested using the poly notation for the embedding to improve this part. But also sometimes poly did better, so they could use deep neural networks or reinforcement learning to predict whether to use poly or reinforcement learning. So here is the main idea. So you have a for loop, and you insert a pragma for the vectorization that has the width and interleaf count. And the agent that they're using, like in other papers, is a proximal policy optimization (PPO), and the reward is going to be the compilation time, code size, execution time, and penalty for overestimating to save compile time, because this sometimes the compilation time to get the reward is sometimes the bottleneck of this type of projects. So the reward, you can see that is normalized against the baseline to get something like the speed up. And the action is basically these factors. So you have a discrete set of factors that you use for the width and interleaf count. And the observation, as I mentioned before, is the loop embedding. And yeah, basically in here you see how the reinforcement learning converges quickly, maybe somewhere around 30,000 samples, while if you use supervised deep neural networks, it takes more than twice time to converge. Also, this kind of this problem is a little bit relatively easy. I mean, you just have a couple of factors. And also an advantage of reinforcement learning is that you can optimize for multiple goals. Some disadvantage that supervised neural networks have, because they depend on gradients. So in here the reward can be something that is not differentiable, and also put multiple goals easily in the reward function. In here you see the comparison between the techniques, and you see that in average the brute force is going to win, of course, because it's like an exhaustive search that cannot really be used in practice. But you can see that close to it is the reinforcement learning option in average. But sometimes poly, for example, wins in this one. Sometimes others, like tree search, wins, but in average reinforcement learning is performing better. So in here you have a couple of benchmarks. One of them is Polybench, for which poly is supposed to be optimized. In here you can see that poly performs better in matrix multiplication than reinforcement learning, but if you combine both, then you get the best performance in average. But also in average, reinforcement learning performs better than poly, but what he's trying to say is that sometimes it could be convenient to combine both. But if you go outside the Polybench, go to MyBench, in this one, reinforcement learning is clearly beating poly in all cases. In this paper, Google Brain and UC San Diego present Relic, which is a reinforcement learning approach for deep learning quantization, and they automatically determine the quantization level of each layer automatically, maintaining the accuracy of the network. So they also use PPO as the reinforcement learning agent, with networks containing fully connected layers and an LSTM for faster convergence. And the networks that they try are AlexNet, LeanNet, VGG, ResNet, MobileNet, and others. And they have a decent speed up over conventional hardware and also over accelerator hardware. And as as is usual in reinforcement learning, the reward is very flexible, so they include accuracy, runtime speedup, energy reduction, and memory, but they give a higher weight on the accuracy because they want to preserve accuracy during quantization. And the action of the environment is going to be choosing the quantization level for one layer at a time. And you can see a picture of the system below. The input is a pre-trained network with a given accuracy and iterate over each layer. And the PPO agent, which has an actor and a critic, are going to select the action, and the action is going to be changing the quantization. They quantize, they run the inference, get the reward, and that's provided to the policy gradient agent for training the networks, and then update the network and keep on going until it gets fully quantized. And here we can see the reinforcement learning environment. that they use. In the upper left, we see the observation space, the state embedding. Some of the properties of the embedding are static, others are dynamic, some are layer specific, others are network specific. For layer specific dynamic, there's the quantization level, which is the one that the action modifies. For a network specific is the state quantization and the state of accuracy. You can see the formulas here. State of quantization is like an accumulation of the quantization across the whole network. You can see that they include memory access in here and other things. For the accuracy, it's basically the current accuracy relative to the full accuracy of without quantization, so they want to keep this to 1. And then you can see in the reward that basically if you go below a threshold, you got a big penalty, you lost the game. And otherwise, the reward of the quantization is mixed with accuracy, so you want to keep the accuracy while trying to quantize as much as possible. And the upper right, you see how to do quantization, two different approaches. One of them is to try all combinations or just change one bit at a time, and they prefer the one in the right because it converges faster. And here we see the results that they got for the different networks. You can see that they try one layer at a time in here for the MNIST dataset from Linet, and they got as training episodes go by, the probability of choosing 2 bits was higher, then 2 bits for the second layer, convolution layer. The fully connected layer got 2 or 3, and then 2. So basically it got 2, 2, 3, 2, and you can see it in here. And you may wonder, okay, but why not just choose 2 for all layers instead of doing all this? But you can see networks like MobileNet in which they get different patterns, or this one like ResNet, and others one that they get different bit quantization patterns for them. And you can see the accuracy loss is pretty low for them. And you can see the runtime results for the Relic tried on a conventional hardware using TVM and the baseline is basically the same, but with a network of 8 bits without quantization, and the runtime speed up is pretty good. And then they tried it on an accelerator with stripes, and you can see that the improvement in speed up and energy reduction for it. In this paper called CodeRL, Mastering Code Generation Through Pre-trained Models and Deep Reinforcement Learning from Salesforce Research, is similar to the one we saw called Execution-Based Code Generation from Virginia Tech. It also uses actor and critic. For the actor, it's going to use a language model, which is building on top of Code T5, which is a previous solution. So now CodeRL is going to be in conjunction with this to further improve the code generation quality. And for the critic, is going to provide feedback on correctness to the actor, and like the one from Virginia Tech is going to leverage the unit test for correctness. It's like a test-driven development strategy, and as we have seen in reinforcement learning problems, this type of problems where you have metrics that are non-differentiable, reinforcement learning is a good solution for them, because if they were differentiable, then probably supervised deep learning training would be good enough. And this is similar to what ChatGPT is doing. ChatGPT basically is a language model that on top of it you get reinforcement learning. So, but this work in particular is focused on code generation. This paper was published in 2022. And you can see that at the beginning they use imitation learning just to warm start the pre-trained language model for up to 10 epochs. And you can see the reward function, part of the reward function below. You can see that the biggest penalty is obtained when the program cannot be compiled at all. You get a slightly lower penalty if you cannot execute the unit test, and basically you get a smaller penalty if the unit test fail, and you only get a positive one on perfection, so if all your unit test passes. And you can see a high level view of the problem here. So you have a problem specification, a text-based problem specification similar to what you provide ChatGPT, but also in addition to that you get a unit test. So the unit test is basically the inputs and the outputs. So these are paired together to make sure that this one, the generated program by the actor, is correct. In this case, we are computing, doing a palindrome computation, and yeah, basically this is gonna be used for training. You can see that the compiler is gonna compile a unit test, which is gonna be providing the reward based on the unit test, and that critic is helping the policy to be trained. So in here you can see that the language model, which is the backbone of the solution, is gonna have a problem and solution. So it's fine-tuned, I suppose, using supervised learning, and it's pre-trained and fine-tuned. And then when you go to the reinforcement learning agent, you're gonna have not only a problem but the corresponding unit test, and that's gonna be used to train the critic to predict the correctness of the program. And also you're gonna provide a solution. Both of them are gonna be used, and the actor in the end is gonna generate the code. And here you can see that the code RL and code T5 outperform the alternatives, GBT based alternatives and alpha code. And this metric is basically the given the number of programs generated for a particular problem. So in this case, we generate 1000 programs for a particular problem, and this is the percentage of success. So it's a tough problem getting these solutions right, so that's why it's so low, but still is better than the provided alternatives. In this paper, they apply reinforcement learning to optimize polyhedral, to do polyhedral optimization. This is from Dresden in Germany. Although they build up on OpenAI Gym, Polyhedral is a different monster, so they basically develop a polygym environment to do optimizations on Polyhedral, and they rely on LLVM and Poly to extract the segments of the polyhedral code, the scopes. It's a concept from Polyhedral, and you can see here that they use Clang LLVM to do that. And they have to break down the problem in two parts. One of them is to get the valid set of schedules that do not break up dependencies, that they have valid dependencies, and then after they get that, after you get the valid schedule space, then you get the optimal schedule, the polyhedral schedule. So this can be broken down into different reinforcement learning agents, although they're showing it as one in here. And then once you get the schedule, then you use Poly and ISL in Python to get the executable and get the runtime to get the reward and keep training. So they were able to improve using the Polybench, the polyhedral benchmark. They improved 3.39 over LLVM with optimization level 3, and they have a 1.83x improvement over ISL. Some of the benchmarks like Hit3D were not able to had to be excluded because of the number of dependencies. As it is expected, polyhedral cannot be used for everything, but when it can be used, it could have a great performance impact. And the reward function is proportional to speedup, but also, as you can see in other work, other things could be added to the reward function. In this paper, they use reinforcement learning to do code generation tasks based on the compiler. That's why it's called execution-based code generation using deep reinforcement learning. So they're gonna, the actor of the agent, they are gonna use PPO, which is a policy proximal optimization, which has an actor and critic. The actor is gonna generate code, it's gonna be compiled, and that's gonna provide the reward that is gonna fit both the actor and critic. So you can see in the reward that the unit tests are very useful for this type of problems, in which you get a positive reward for each unit test passed, and negative for failing unit test, and bigger penalty for compiler runtime error, and also you get an additional penalty for not compiling at all. Okay, so the PPO coder is what the coder project is, combines existing programming language models with the PPO agent, and employs execution feedback from the compiler. The code generation tasks include code completion, code translation, and code synthesis. And the languages are C++, Java, Python, C#, PHP, and C. And they improve the baselines, as we're going to see in a moment. And as in the case of a compiler gym, they're going to model the problem as an MDP, Markov decision process. And basically, yeah, that's what they do. So here is a more detailed picture of the internal components, and you're gonna see that they have the actor and the critic, and they're gonna have a loss based on the actual value and the reward, because the value, as in any reinforcement learning agent, is gonna try to predict the long-term reward. So that's why you're differentiating there. In here you compute the gradient, although it's not very clear how they compute the gradient to optimize to improve the reward, to get a better reward. And here you can see that they generate code and they use the data flow graph representation, the syntax tree. They use both of them, and they have a match score in here, but also they have the compiler feedback, and everything is added into the reward. And also they have a references pre-trained model to help training the agent. So in here you can see the performance comparison to other code generator projects, and the similarity and match are improved slightly. But the most impressive part is the compilation rate, since they're including the compiler in the loop. Now the success rate of compilation is way higher than the other alternatives. Of course, if you want to make a code generator, you have to have 100% compiler rate, compilation rate. Otherwise, you get a bug. So basically, you get a 2.32 probability of getting a bug. So this is not good, but it's quite close of 100. So it's pretty impressive. So in here is the results for each programming languages. The columns are the source language and the rows are the target language. So let's say, for example, if you're going from Python to Java, which are two pretty high level languages, you get the best success rate. Or if you get from Java to Python, also you get a big success rate. But this is not good. The compilation rate, you have to get 100%. But now things get more complicated when you're going from a high level language, let's say, to a lower level language like C++. You get a compilation rate, a compilation rate 63. This is pretty bad. You have to get 100%. So if you go from Java to C++, it's almost the same. But now things get worse if you get into a lower level compiler. Let's say from Python to C, you get 50%, and you go from Java to C as well, or C++ to C, is pretty bad because it's very low level. Here's some ablation studies that they made because they combine various techniques, so making sure that all of them contribute to the optimal performance that they're getting. So here you can see when you're going from Java to generated C++ code, the improvement that a PPO coder plus the existing programming language model is having over just the programming language model. So when this language model is trying to generate C++ code from Java, you're gonna see that this array list only has one element, but here you get two, and it even gets the wrong wrong container. So that's a compilation error. And here you have got a syntax error. The parenthesis is gone. But here is worse because you're trying to push the J index into the array, and here it is pushing I, which is an argument to the function. This is a silent wrong answer, which is worse. So in here you got the tree right. You got the vector in here, as you expected. You get the parenthesis, and also you get the right J into the array. In this paper, they present Chameleon, which uses reinforcement learning to optimize deep neural networks. They basically improve the auto TVM, autoscaler from TVM, and they improve our algorithms of evolutionary search and simulated annealing, and they achieve a good performance improvement, runtime performance improvement. But the key takeaway is improving the optimization time. And because in these schemes, to get the optimal configuration, they have to measure the performance, the runtime performance of the network in a particular hardware, which takes time, and that becomes the bottleneck. So reinforcement learning is wiser in choosing the samples to try. So that reduces significantly the number of times that you have to go to the hardware to get the runtime performance and compute the reward. Here are the references that were used in this video. We covered all of this here and the first two in here, and you can see that optimization order is a very popular use of reinforcement learning, and you can find all these references in the description of this video. Here are some takeaways that I got from the papers that we went through. We saw that there's plenty of work demonstrating that reinforcement learning is very effective and practical for various compiler optimization problems. There are existing tools out there that facilitate the integration of reinforcement learning with compiler optimizations like CompilerGym, Supersonic, PolyGym. We saw also that PPO is one of the most popular agents for these reinforcement learning problems, which is the same agent that was used for ChatGPT. But also MCTS and A3C are used. The reinforcement learning agents, once they are trained, they are fast. They should be fast on inference. Also, we saw that reinforcement learning agents are good for and efficient for in sampling. They wisely choose the samples compared to alternative methods, so they tend to converge faster on training. Reinforcement learning agents also are portable. You can easily train them for multiple targets and optimize for those targets, hardware targets, without knowledge of the actual hardware target. And also the reinforcement learning agent rewards are easy to set up, and they're capable of modeling multiple nonlinear goals at the same time. Thank you for watching.